Welcome to you, our listener, to today's deep dive. Our mission today is to unpack and, well, really decode the secret mathematical engine that silently runs our modern world.
Yeah, it's everywhere.
It really is. And we are working from this dense, highly technical, but fundamentally world-changing set of source material titled Day 32, Conditional Probability and Bayes' Theorem.
Right. It's a heavy title.
It is a very heavy title, but we're going to take the raw mathematical logic outlined in this text and explore how it applies to like three wildly different engineering fields. So we've got aerospace, electronics, and software, and then we'll look at how a computational simulation engine actually tests all of this against reality, because it is an absolute masterclass in how we navigate uncertainty.
Absolutely.
Because when you think about it, when you pick up your phone to make a call, or when you check your email, or even when you just look up at the sky and see a commercial airliner passing safely overhead, there is this immense illusion of absolute certainty.
Right. You just assume it works.
Exactly. You just assume the phone perfectly transmits your voice, you assume your inbox magically knows what a spam message is, and you assume an air defense radar can automatically tell the difference between a Boeing 737, a flock of migratory birds, and an incoming hostile missile.
Yeah, we just experienced the flawless end result.
Yeah.
So we naturally assume the underlying process must be completely clean, binary, and absolute. Like it's either a bird or it isn't.
Right. But if you actually lift the hood on these systems, you realize that the real world is incredibly noisy.
Oh, it's completely chaotic.
Yeah.
There's physical clutter in the airspace.
Yeah.
There is static and heat inside our phone lines. There are deceptive, ever-changing tactics in our emails. The systems we rely on to survive and communicate aren't operating on pure certainty at all.
No, they're not. They are operating on probabilities.
And making that transition, taking the chaos of the real world and distilling it into a reliable, actionable decision, it requires a very specific, highly sophisticated mathematical engine to filter out that noise.
It does. It's a massive filtering process. I am honestly amazed that a single mathematical concept can span across so many vastly different industries. But it's a lot to wrap your head around.
Okay, let's unpack this. Before we get into the advanced algorithms stopping missiles or catching hackers, we have to start with the bedrock logic from our sources.
Yeah, we have to lay the foundation.
Right. So how do probabilities actually change when new information is introduced?
That is the perfect place to start, because before you can build a multi-million-dollar radar system, you really need to understand the structural logic of what we call conditional probability.
Okay.
In its simplest definition, conditional probability is the probability of an event, let's call it event E, occurring, given that another event, event F, has already occurred.
Okay, let me pause you there. The key word being given, right? So event F is already a locked-in reality. We aren't guessing if F happened. We know it happened.
Precisely. You have new information. And mathematically, this structurally restricts your sample space.
The formula in our source expresses this as the probability of E given F equals the probability of E intersecting with F divided by the probability of F.
Okay, I want to make sure I'm visualizing this correctly without getting totally lost in the algebra. By restricting the sample space, we are talking about changing the boundaries of reality for our math problem, right?
Mm-hmm. Yes.
So if event F happens, our whole universe of possibilities instantly shrinks just to the new boundaries of F. All the other possibilities outside of F are just gone. They vanish from the equation.
Yes, that is a highly accurate way to visualize it. And what's fascinating here is that this simple restriction of the sample space is the absolute foundational building block for all predictive logic and engineering.
Wow.
By the probability of event F, you are essentially normalizing your new universe. You are saying, okay, event F is our entire world now. Within this new, smaller world, how likely is event E?
So what does this all mean for how different events interact with each other out in the real world?
Well, it creates a crucial distinction between two types of events. You have independent and dependent events.
Okay.
Two events are strictly independent if the occurrence of one does not alter the probability space of the other at all. Like, if I flip a coin and you roll a die, my coin flip doesn't shrink the universe of possibilities for your die roll.
Right, they don't care about each other.
Exactly. And the math reflects this. To find the probability of both happening, their intersection, it scales linearly.
Yeah.
You just multiply the probability of event E by the probability of event F. Simple as that.
Because neither one affects the other, but dependent events would be like drawing cards from a deck without putting them back.
Exactly.
If I draw an ace, the universe of the deck has structurally changed. The odds of you drawing an ace on the next turn are totally different now.
Exactly right. For dependent events, the multiplication theorem fundamentally relies on that conditional state. To find the intersection of dependent events, you multiply the probability of event E by the probability of event F given E.
Given E, right?
Because they are entangled. The outcome of one actively alters the probability space of the other.
Okay, so knowing how events restrict possibilities moving forward is our baseline. But this naturally leads us to the next massive question, and really the core of today's deep dive.
Yeah.
If we can use math to predict an outcome based on a condition moving forward, how do we use this math to work backward? Like, how do we start with a known effect, something we just witnessed, and work in reverse to find its unknown cause?
And that brings us to the crown jewel of our source material, Bayes' theorem.
The math of reverse probability. But before we get into the heavy terminology, give me a tangible example. How does this actually look before we attach all the math terms to it?
Sure. Think about a warning light on your car's dashboard.
Okay.
That warning light turning on is your observed effect. Now, you need to work backward to find the cause. Did a major engine component fail? Or did a tiny $10 sensor just glitch out?
Right, which happens all the time.
Exactly. Bayes' theorem provides a rigorous mathematical framework for calculating the probability of a specific cause, given that you are currently staring at a specific effect.
I see. So as a driver, I know that sensors glitch out way more often than entire engines explode. So I already have a baseline guess in my head before even taking it to the mechanic.
And that baseline guess is the first of three critical components our sources outline. It's called the prior probability.
Prior probability, okay.
It is what you know about the state of the world before you see any new evidence.
Okay, so prior probability is my baseline. Engine explosions are rare. Sensor glitches are common. What's next?
The second component is the likelihood. This is where you evaluate the evidence itself.
Okay.
It asks, if the engine really was exploding, how likely is it that it would trigger this specific warning light? Or conversely, if the sensor was just glitching, how likely is it to trigger this exact light?
Okay, that makes sense. You weigh the evidence against the possible causes.
Which leads to the third component, the output of Bayes' theorem, the posterior probability.
The posterior probability.
Yes, this is your updated belief. You take your prior baseline, you factor in the likelihood of the evidence you just saw, and the math spits out the posterior probability, which is the newly updated certainty that your engine is actually failing.
Wait, so posterior isn't just a fancy math term. It literally just represents our newly updated belief after we actually look at the evidence.
That is exactly right. It's the after picture. And if we connect this to the bigger picture, Bayes' theorem is not just a formula to memorize. It's a mathematically formalized way of changing your mind based on new evidence.
Whoa.
It allows an engineering system to continuously, rapidly update its beliefs without guessing.
A mathematical formula for changing your mind. Now, the source material also mentions a major constraint here. For Bayes' theorem to work, it requires a set of mutually exclusive and exhaustive events. What does that actually mean in plain English for a dashboard warning light?
It means that all the possible causes you are evaluating must form a strict partition of your sample space.
Yeah.
Mutually exclusive means they can't overlap in your calculations. Exhaustive means you have accounted for every possible cause. There is no hidden cause C that you forgot to include.
Right.
If you have those conditions, you sum them all up in the denominator of Bayes' equation, and you can pinpoint the exact reverse probability of any specific cause.
Okay, so we've established the structural logic. We have our formula for reverse probability, and we know how to update our beliefs mathematically. Now, let's take this out of the theoretical realm.
Yeah, let's look at the real world.
The source text gives us some incredibly tense scenarios where this is physically implemented. Let's start with massive hardware and sensors in aerospace engineering. Radar target identification.
Imagine an air defense radar scanning a coastline. It detects an inbound object.
Okay.
That detection is our observed effect. The radar system must instantly classify this object into a set of mutually exclusive and exhaustive categories.
Right, like we just talked about.
Exactly. Let's say event E1 is a commercial airliner. Event E2 is a flock of birds. And event E3 is a hostile inbound missile.
Talk about high stakes. I mean, it cannot get this wrong.
It absolutely cannot.
Yeah.
So how does the radar decide? It doesn't just guess based on one blip on a screen. Here's where the math comes in.
Okay.
The radar computer holds prior probabilities based on massive amounts of historical flight corridor data. It knows the baseline probability of an airliner being in that exact patch of sky on a Tuesday afternoon versus a flock of birds or a missile.
Here's where it gets really interesting. So the radar isn't just blindly looking at the object right now in a vacuum. It's actively weighing what it sees right this second against the historical baseline reality of what usually flies in that exact corridor.
It has to, because relying purely on raw sensor data in the moment can be extremely deceptive.
How so?
Well, a dense, tightly packed flock of birds might briefly bounce radio waves back in a way that looks like a larger metallic object. So when the system observes a specific radar cross-section, the RCS, it applies Bayes' theorem.
Walk me through that. What is it actually doing with the radar cross-section?
The radar cross-section is the evidence. It's how big the object appears based on how the radio waves bounce back. The radar takes that new evidence, and it continuously loops it through Bayes' formula to update its prior probability into a posterior probability.
So it's constantly crunching the numbers.
Sweep after sweep, millisecond after millisecond, it calculates the mathematical probability that the target is a missile. This active filtering is what prevents terrifying false alarms, or conversely, delayed interceptions.
That's incredible.
Combining historical priors with real-time likelihoods is what prevents catastrophic errors in a chaotic airspace.
It is constantly changing its mind, refining its belief every single time the radar sweeps. That is brilliant. Okay, so that's how we find certainty with a massive physical object in the sky. But what happens when we shrink this down to the microscopic level?
Right, going from massive to tiny.
Yeah, how does this same math apply to invisible digital bits flying through a wire? Because our sources outline a totally different hardware application, signal decoding and the bit error rate in telecommunications.
Shifting to digital telecom, we look at how data physically moves. Whenever a transmitter sends out a stream of digital data, say a text message or a piece of a downloaded file, it's sending a rapid sequence of ones and zeros, electrical pulses.
Okay.
But the channel between the transmitter and the receiver is never perfect.
Because of the chaos of the real world again? But wait, hold on. If a wire is just a copper pipe sending electrical pulses that represent ones and zeros, how does a zero accidentally become a one? Like, what is physically happening inside that cable to cause that?
It usually comes down to thermal noise and electromagnetic interference. Even the simple physical heat of the copper wire causes electrons to bounce around erratically.
Wow, really? Just the heat?
Yeah, just the heat. This jitter creates electrical noise. Sometimes that noise surges at the exact microsecond. A zero, which is a low voltage signal, is passing through.
Oh, I see where this is going.
The surge spikes the voltage artificially, and when it reaches the receiver, it looks exactly like a 1. The bit has literally flipped during transit.
Wow, okay. So the receiver on my phone gets a 1. But because of this thermal noise, we can't be 100% sure that the cell tower actually sent a 1.
Right. This is the receiver's dilemma. It has an observed effect, it received a 1. But what was the cause? Was it a legitimate 1 or a corrupted 0? This is where the receiver logic utilizes Bayes' theorem.
Okay, how do they do that?
Telecommunications engineers map out the known physical noise profile of the channel. They calculate the exact likelihood of receiving a 1 given that a 0 was transmitted.
I see. They build a mathematical profile of the cable's flaws.
Exactly. The receiver references that known noise profile, factors in the prior probability of 1s and 0s being sent in that specific encoding scheme, and calculates the exact posterior probability that the original bit was actually a 1.
So even when our digital calls or downloads get scrambled by physical heat and static, this Bayesian math engine is quietly sitting inside the receiver chip, working backward from the scrambled mess to reconstruct the original data. It is finding certainty within statistical noise.
It is correcting reality on the fly, thousands of times per second.
Okay, so we've covered the macro with aerospace hardware and the micro with the telecom hardware. But hardware has physical limits. How does this logic scale when we move into pure software where we are dealing with millions of data points simultaneously?
Right, because the scale changes entirely.
Yeah, because our sources highlight a massive domain here. Cybersecurity, specifically spam filters and network intrusion detection using naive Bayes classifiers.
When you scale this up to software, you need incredible speed. A naive Bayes classifier in an email server analyzes network traffic using the exact same principles we just discussed, but scaled up exponentially.
Walk me through a spam filter. How does Bayes actually catch a bad email?
Well, the software engine starts with a prior probability. It knows historically what percentage of all incoming email to that server is spam. That's the baseline. Then it starts reading the incoming email packet. If the email contains a specific payload or keyword, let's say the phrase unauthorized access, that is your evidence. The filter calculates the posterior probability that the email is spam, given that the keyword is present.
Wait, hackers are smart. If they know we are using this exact math to look for keywords like unauthorized access, can't they just manipulate the keywords, like change access to AC33 to break the math?
Oh, they absolutely try. And if the filter only looked at one word, the hacker would win. But a naive Bayes classifier doesn't stop at one keyword.
It looks at more.
It looks at hundreds, sometimes thousands of parameters simultaneously. The sender's IP address, the time of day, the formatting of the headers, and thousands of other words.
Oh, wow.
By mathematically multiplying the conditional probabilities of all these individual pieces of evidence together, the engine determines an overwhelmingly accurate overall probability. It builds a mosaic of guilt.
A mosaic of guilt. I like that.
Yeah, so even if the hacker obscures one word, the cumulative posterior probability of the other 999 factors will expose the email, allowing the server to instantly drop the packet.
It's mathematically weighing every single word to update its belief about the email's true nature. That is incredibly robust. Okay, this brings up the final section of our source document, which details a computational proof.
Right, the simulation.
Exactly. It describes a factory defect tracking simulation. We have 3 distinct assembly lines in a simulation, each producing millions of parts, and each line has a slightly different known error rate. The simulation randomly pulls a defective part from the massive pile and then verifies the theoretical Bayesian probability of which line it came from against the raw empirical data. But I have to push back here for a second. If Bayes' theorem is a proven mathematical law, like we've been discussing this whole time, why do we need a massive simulation engine running millions of parts just to validate it? Is empirical reality somehow messier than pristine math?
This raises an important question, and it really speaks to the very heart of engineering. In pure mathematics, Bayes' theorem is perfectly true. It is an undeniable logical law. But in engineering, a theoretical model is only as good as its mapping to the physical world.
Because reality doesn't always behave perfectly like a textbook.
Exactly. An assembly line might have fluctuations in power, a machine might wear down at an uneven rate, the temperature in the factory might affect the materials, right? Running a computational simulation with millions of empirical data points isn't about proving that the math equation works. It's about validating that our assignment of prior probabilities and likelihoods actually matches the raw, messy behavior of the factory floor.
Ah, I get it. The math will always give you a perfect answer based on the numbers you feed it. So you have to simulate it to make sure you are feeding it the right numbers.
Precisely. We have to ensure that our theoretical models map onto empirical reality perfectly, or else our posterior probabilities, our final decisions, will be dangerously wrong.
That makes total sense.
The simulation proves that the theoretical logic holds up under the weight of massive, real-world data loads and physical variances. It basically keeps the math honest to reality.
Well, let's recap this incredible journey for you, the listener. We started with the foundational concept of restricting a sample space, changing the boundaries of what is mathematically possible based on the conditions of what we already know.
Right.
We learned how Bayes' theorem works backward, moving from an observed effect to an unknown cause. And we saw how engineers use this exact same mathematical engine to do completely different things, decoding corrupted digital bits caused by thermal heat, identifying inbound missiles by updating radar sweeps, and filtering malicious spam out of our inboxes by building mathematical mosaics of guilt. Bayes' theorem truly is the hidden architecture of certainty in an incredibly chaotic world.
It is the ultimate filter. And the reason this matters to you listening to this right now is because this isn't just for machines and radar arrays.
Not at all.
Every single day, you are bombarded with evidence. You consume news, you navigate complex social interactions, you take in data from your environment. You are constantly forced to update your baseline assumptions to find the truth.
Understanding how engineers use this math to filter out noise can actually help you think more clearly and more objectively in your own life. It teaches you to actively weigh new evidence against a historical baseline, rather than just reacting emotionally to the loudest signal in the room.
It provides a formalized, logical framework for rational thought.
Which brings me to a final thought I want to leave you with today, something for you to just mull over on your own. The sources we went through today showed us how machines, radars, and software computers use Bayes' theorem to update their beliefs based on incoming evidence. But think about your own brain.
That's a fascinating angle.
When you meet someone new for the very first time, aren't you essentially just starting with a baseline prior probability based on your past experiences with people? And then with every single word they say, every gesture, every action, aren't you constantly updating your posterior probability of who they are and what their intentions are?
You're doing the math without realizing it.
Exactly. What if human intuition isn't magic at all? What if intuition is just Bayes' theorem, running natively in the wetware of our minds?
That is a profound way to look at it. We might all be Bayesian engines without even realizing it.
Let that sink in. The next time you immediately sense that a situation is wrong, or that an email is deceptive, or that the static on a phone call is clearing up, just remember, you are calculating probabilities. You are finding certainty in the noise. Thanks for joining us for this deep dive.